before I start the lecture, which our first module is binary representation. Here. That would be a good time to start the camera.
Yeah, no, I did.
All right.
We had a crisis, but he solved it.
Before I start, I want to bring back one of the problems from Wednesday, Thursday, the one with the square game. Remember, there's a bunch of squares, and that was the first board. And the idea is each player here can take out pick a row. Say I pick this row, and I take out a bunch of squares from it. Almost all of you came to those recitations, so I'm sure you know the game, right? And that's me, and then the next player comes in, can pick another row here, and say take this piece out. And we keep going until one player takes the last piece, and that person wins the game. So we said, this is just a recap. Here's some boards for player B to win. Formally we say 100% winning strategy. One is the mirror board. If rows are in a mirror, for example 2, 1, 1, 3, 3, and 4, 4. Not really squares. This is mirror to each other, mirror to each other, mirror to each other, mirror to each other. We said at recitation, player B has an obvious strategy of winning, which is on this board, I let my opponent do something, and whatever my opponent does, I repeat the same move on the paired row, which means eventually I'm going to win the game. Another one was the 1, 2, 3 board that can be verified manually. In here, player A does whatever move. The next move, which is player B, will bring it to some form of mirror, which is a winning situation. So those are the cases we talked about. Now, what we want to get in here, which we're not going to get to today, but we will get in about 3 weeks, is what is the overall strategy. I can put up a few boards, and for each one of these boards, I'm sure we can manually find a winning strategy. We can say that player wins, so that player wins. But what about the general board? Any rows, any squares, so on and so forth. So, although in terms of practically playing the game, being smart and figure out things quickly might help, this game has what's called a closed solution. A closed or analytical solution is that we don't have to try things and compute things in advance. That's how computers play chess. All we have to do here is compute a certain function, and that function will tell us exactly, without doing any moves, who has a winning strategy 100%. That function relates to binary and relates to another thing. So the function we need of the board gives us the outcome depends on binary representation and the sort function, which we haven't studied yet, but maybe some of you heard of sort function. How many people heard of sort function? Hands up. Oh, almost everybody. So it's not a problem if you didn't, because we're going to do it in class in those 2 weeks. But if you can solve this problem for me before I get to it in 3 weeks, aka told me what the function is that I need to compute on this board, how to represent in a computer function, and get the result, and how that result tells me who wins the game, you get a cookie. That's extra, so we don't get points for the homework or grades. We get the cookie. If you tell me the second part, which is not just who wins the game, but what is the strategy. If you tell me player A will win the game, or player B will win the game, well, fine. Well, what does player A or B have to do, depending on the opponent, of course, to win the game? You get another cookie. That strategy will be in here. We can tell player B is going to win, right? But we can also specify the strategy. How does player B win? it repeats the move of player A on the pair draw, right? How many people follow me on this mirror board? And that's the strategy, right? If I repeat player A on the mirror board, I win. That's the winning strategy for player B. So I want two things. I want a computer function that tells me who wins, but the harder part is to say, okay, now that I know player A wins, or player B wins, how I define a strategy and write it down on a piece of paper to say, here's how I win. Okay? That was a quick recap. Now we have to get to the real stuff. Real stuff. Where to start? Where should we start? Intro to mathematics for computer science. Any idea where to start?
Binary representation.
Yeah, but how do we start that? I have written here in some notes. We start with an addition. Let's see if we can do that. You guys know how to add numbers, right? This is a regular credit, so you can tell how far we went down from an interesting thing to a pure addition. Sounds familiar? Like second grade, maybe? Yeah, that's where we are. So how do we add up numbers? 2 plus 6? One, and we put here a carry, right? That means I've had a 1 from before. You guys laughing at me? I did something wrong?
No.
So it's too easy, right? This is a 9, right? Because 1 plus 7 plus the carry, and then 8 plus 3 is a 1, and then I get another query here that adds to 0, 0, right? There's nothing here on the 4th bit, so I get the carry, right? Good. So how did that actually work? Of course, that's a procedure to do it. Doing it this way gives you the correct answer, but why is that? That's the story with those binary cards. It's not too hard to figure out those binary cards. What did I do? Remember when you give me the cards and I tell you what number you thought of? I just added up the corner numbers, right? Several people figured that out, actually quite a few people. But there's another question. Why did that work? So the same thing happens here. Procedurally, we do that. But why is that true? So then to figure that out, we write these numbers properly represented in base 10, because they are in base 10. In base 10 means the numeration base that acts with exponents is 10. What I mean by that is this is 8 times 10. This is the thousandths digit. Thousandths being 10 at what power?
3.
Plus the hundredths digit, which is 10 to the 2, plus 9 is the 10th digit, 9 times 10, plus 2 is the unit digit, which is 10 at what power?
0.
Very good. So 10 at 0 is 1. Hands up, who knows that? 10 at 0 is 1. Very good. Again, this is the thousands digits, 100 digits, 10 digits, and 1 digit. How about the other guy?
3 times 10.
3 times 10 to the third plus
1
times
10
10
squared.
to the 2 plus 2 times 10 plus 6 times 10. Okay, so how did the addition work? We say, how many tens at 0 we have? 2 of them. And then this other person, guy, comes with 6. So 2 plus 6, that's 8 of these digits. How about in here? We have 10 at 1, right? This is the tens here. So we have 9 oranges plus 2 oranges. That's 11 oranges. Right?
Yeah.
Only 11 I can't write as a digit in base 10. Right? So I took this answer 11 and I say, wait a minute, 11 is really a 1 here and plus a 10. Right? So what I did, I write that 1 here. So I say 1 times that. But I have another 10 that moves in here, right? So in here when I did the addition, I've got 7 plus 1. Those are 8 of these guys. Those are not oranges. Those are apple now, because they're different kind. 10 to the 2. Right? And this 10 here is also a 10 to the 2 now. Because these oranges were 10 to the 1. 10 oranges is 10 times 10 to the 1 makes a 1 apple. Let's make sure we follow that process. Where does the carry bit comes from? It comes from adding the tens. I've got 11 tens. I'm going to write one of them. I'm going to keep 10 times 10. That's a 1 apple because apples are hundreds. So I get 8 here plus this value. So I get 9 times squared. And then of course, the same thing happens here. I get 1 times 10 to the sum of those two coefficients, 8 and 3, is 11. So I write the 1. The 10 times 10 to the third gives me the 10 to the fourth. This stuff in here, it was 11 times 10 to the third. That's why the carry bits act that way. The fundamental principle that make it work is to figure out that 10 of those things, I have 11 total, I write 1. 10 of those things times the base, 10 oranges makes an apple. That's where that's the principle of the carry bit. 10 times 10 to the 1, it's 1 times 10 to the 2. That's why we added this 1 in here. That has to do with how the numeration base work. Because they always have this, there's the base 10, and they have these exponents. And the exponents are precisely designed to work in that way. If I get 10 of this guy, I get this. If I get 10 of this guy, I get that. If I get 10 of these thousands, I get the next power, 10 to the fourth. That's not just in base 10. This principle applies to all bases. So in here we have base 10. So in base 10, the digits are 10 to the 0, 10 to the 1, 10 to the 2, so on and so forth. The principle is that 10 at some power times 10 is 10 at the next power. Of course, that's what makes the carry bit. And the digits are, in base 10, will be, so those are the locations, and the digits will be 0, 1, 2, up to 9. The reason I can only go up to 9 is that if I have 10 of these, I get to the next power. Okay? So how do we do the same thing in base 2? I want to show you base 10 because that's what everybody's familiar with.
Do you want us to answer what we think about this?
No, I'm just going to do it. That's easy enough. I think everybody's going to follow. So we don't want to do those numbers because they're too big to do in base 2 for now. So in base 2, we're going to do something like, how about this value? 1, 0, 1, 1, 0. So that's base 2 now. In base 2, what's going to happen? The powers would be 2 at 0, 2 at 1, 2 at 2, 2 at 3, so on and so forth, right? The digits will be same principle like in base 10. I can only go up to a value that represents the power, so those would be what? 0 and 1, right? Because 2 is the power, I can't go there. And the principle of the carry bit is what? 2 at some power, any power, times 2 is 2 at the next power. Just like in base 10. So as a representation, how would this work? This corresponds, this one here. By the way, this is the least significant. Just like in here, this is the least significant. Let's just say least significant bit or digit. And this is most significant. So this digit here, 0, corresponds to what? What power of 2? 2 to the 0. So that's this guy. How about this 1? Corresponds to what?
2 to the 1.
1 is the digit times 2 to the 1. How about this one? It's 1 times 2 to the 2. How about this 0? 0 times 2 to the 3. And this 1 here is 1 times
2 to the 4.
2 to the 4. Procedurally speaking, every digit in every base, say this 8 for example, we know it's going to multiply with 10 at the power because it's base 10. The power is how many digits are after it. So this 8, how many digits are after it? 3. When I multiply it, it's going to be 10 to the 3. How about this 2 in here? It's going to multiply with 10 at the power because it's base 10. What's the power? It's how many digits are after it. So all of 1. Same thing in here. This 1, I could tell from the beginning that's going to multiply with 2 at what power? 4, because there are 4 digits after it. Okay? So now, as a quantity, quantities are independent of bases. That's a confusion a lot of young students do. Quantities are fixed. Bases are just a representation of those quantities. We can represent any number in any base. So I can tell what's the quantity in base 10, right? I can add up those things. 2 to the 4th is 16. 2 to the 2 is 4, and 2 is 2. So this is 22 in base 10. Because I wrote these quantities now in base 10. Now, this is a fixed quantity. Either this or this means the same value. It's just represented in different bases. And that's not just base 2. I could do it in base 4. Same quantity. How would I write this in base 4? Now, in base 4, what are the digits? So base 4, the powers are, of course, 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. The digits are
0, 1, 2, 3.
0, 1, 2, 3. I can't use 4 or 5 as a digit because that breaks the base. And the carry acts like what? 4 at the power times 4 is 4 at the next power. So if I am to take this number 22 and represent it in base 4, not in base 2, what do I do? See, if you look at these decompositions, you have to decompose it into the power of that base. So in base 4, just informally, 22 in base 10.
1, 1, 2.
There's a funny thing going on here.
It might be movement based and we're just not like moving enough.
You think I'm not moving enough? Yeah?
You can just do a little jig every now and then.
A little dancing.
Yeah.
Yeah. We need to call not today, but we definitely want to call the whoever to fix it. So what are powers of 4 that I can get in here? 16.
4.
16 is 4 to what power?
Square power.
Square. And how many? Remember in base 16, in base 2, it's either 1 or 0, the digit. So it's either there or not there, right? In base 4, it's not just there or not there. How many? What are the possibilities for a digit in base 4? It could be there as in 1 time, or 2 times, or 3 times, or not there at all. In base 10, there's even more possibilities, right? In base 10, it's not there or not there. It's not there, or 1 time, 2 times, 3 times, 4 times, so on and so forth. So this 16, how many times is in 22? 1. What's the next power of 4 that fits in 22?
4.
4 at the power 1. How many times it fits? Once. And then the next power is 4 to the 0, which fits, that's a 1. So I got 16 plus 4, that's 20. How many 4 to the 0s do I need to add to it? 2, right? Because 16 plus 4 plus 2 is 22. So what is this in base 4 now? 1, 1, 12, base 4. So this principle that you guys are extremely familiar with in base 10, it's reflex, I'm sure, for most of you to add and subtract and represent numbers in base 10. Something like this, virtually everybody who graduated secondary school can do. That principle applies in all bases. Of course, for computer, base 2 is the base that they use all the time. So everything will be represented in base 2. Now, for certain calculations, computers can do very, very well. In fact, they facilitate calculations in base 4 and base 8. The reason for which computers do very well in base 4 and base 8 and base 16 too. They are powers of 2. 2 is the physical, electrical representation, as in, if you look at a piece of memory, for example, those sticks that you've seen, the green ones with chips on them, right, memory. The way they represent stuff with ones and zero is for each little cell, billions of cells in there, either electrical current passes through or it doesn't pass through. That's the representation of memory, right? And it only works if you have electricity. If you shut down your computer, that RAM memory, right, DDR, it's gonna shut down because there's no electricity, it dies. As opposed to a hard drive that also represents things in 0, 1, but you can turn off the power and still have the data on the hard drive. So the old hard drives that have rotating disks have a magnetic way to store those ones and zeros. The solid state drives, hard drives, have a different mechanism. Nevertheless, every one of these devices, whether it's RAM memory or solid state drives or hard drives or tapes, have a way of representing ones and zeros. Now, if that's the physical representation, of course, from that base, I can easily get calculations in base 4 and base 8. The reason is, base 4, it's simply reading 2 bits at a time. I can get anything from base 2 in base 4 by taking 2 bits in base 2, making 1 bit in base 4. We'll get to that next week. That those bases, calculations between them are extremely easy because it's a very mechanical calculation on the bits themselves. We don't have to do this transformation. So computers can do easily those bases, but not so easily base 7. For base 7 or base 9, they will have to do what we do, to transform numbers from one base to the other. So for fun, let's just do 22 also in base 8. If I am to repeat this process in base 8, what's the first power of 8 that fits in? 8 to the 1, right? How many times?
2.
2. And then it's 8 to the 0. How many 8 to the zeros, that is ones, I need to put in to get to 22? This is 16. I need a 6. So the representation in base 8 will be 26. Okay. Who followed me so far? Hands up. Very good. Okay. Here's some other examples here. Let's take some more. 41 in base 10. When we work with this basis of numeration, aka where the base is not fixed, usually when you write, math, you don't specify the base because everybody knows you're writing base 10, right? But when we transform from one base into another, it's necessary to write the base. For some numbers like 41, it's a valid number in base 10. It's also a valid number in base 8. Right? 41, it's a valid representation in base 8. If I wouldn't say the base, it would be a little ambiguous. It's that in base 10 or in base 8. Is this a valid representation in base 4?
No.
No. Because, so I would know it's not base 4, but I wouldn't be sure it's base 8 versus base 10. That's why when you do these kind of calculations, you have to specify the base. So in base, if I am to transform this in base 2, so for the rest of the lecture today, I'll abandon base 4, base 8, and base 16. I'll come back to that next week. So we only stick to base 2 now. How do I do this in base 2? I do the same kind of calculation. What's the biggest power of 2 that I can take out?
30 to the fifth.
Which is 2 to the
Fifth.
fifth. In base 2, I don't have to worry about digits. Like I figured out here how many of these 8s are coming out. In here, in base 2, if it's the digit there, the coefficient must be 1, right? Because it's only 1 and 0. So that's 1 times this, plus what's the next power? 2 to the 4th, would that fit in?
Nope.
No, so let's say 0 times 2 to the 4th. 32 out of 41, I get 9. So what can I fit in 9? 8, that's 2 to the 3rd, right? And then what do I have? Do I have 2 to the 2s?
No.
How about 2 to the 1s?
No.
No. And then I get 1, 2 to the 0, is that right? So this would be in base 2 what? 1, 0, 1, 0, 0, 1. Is that true? Now, I could add to this, I could say add a bunch of zeros in front of it. It wouldn't change the values, right? I could add any number of zeros I want. And that's important for computers because when you represent a number with the computer, you not just have to give the representation. You have to specify how many bits you want to use. So computers understand 10100 represented on, say, 8 bits, like that. Or they could understand 1010001 on 16 bits. That would be having a lot of zeros in advance, in front of it. So for computers, in some programming languages, for example, you have to be very clear on how many bits are you using. Those formal languages that ask you to declare variables. When you declare a variable, one of the things that you do is decide how many bits are you using for those numbers. Integers, for example, are typically represented on 32 bits, right? So when you say int, in most programming languages, not all, but in most programming languages, when you declare variable an integer, it allocates 32 bits for it.
Does that affect like the efficiency the program runs at all? Like if you chose to use like a 16-bit data type, would it run
It
faster?
affects calculation. I'm not sure what you mean by efficiency.
Well,
RAM,
it would
which
go
is
slower.
the RAM, the computer memory, also the processor registers, they have random access, as opposed to the old hard drives that do not have random access, right? A hard drive or a tape, to get to a certain position on a tape, I have to roll the tape to that position. With a hard drive, I have to spin the head to get to that spot. SSDs and RAM and CPU registers, where the calculations happens, they have random access. So no matter how big it is, it's equally easily to get to this spot or that spot. So in that sense, whatever number of bits you have, getting to some place, it's the same. However, of course, adding 32 bits registers takes more operations than adding 16 or 8. That is particularly important for graphics cards, not for CPUs. For CPUs, the cores of the CPU, Intel cores, like get the 6-core CPU type of thing, they're very complex. They can do 16-bit and 32-bit roughly in the same way. Graphics cards are very simple cores, but they have a lot of them, right? You get the graphics card, you get 3,000 cores, but each core is very simple. Because they are simple, there are different cores for 16-bit and different cores for 32-bit and different cores for 64-bit. In a CPU, the core does all the whatever representation you have, does the operation. In a graphics card, you're going to notice that a computation graphics card, like an NVIDIA Tesla, comes with more core for 64-bit computation, because that's what it is for, right? An NVIDIA Tesla graphic card is for CUDA computation, and scientists use a lot of 64-bit representations, say for atomic physics, and they need a lot of 64-bit cores. But the regular graphics card that's for gaming doesn't need so many 64-bit cores, because all the games work in 32 or even 16 bits. For games, it's not necessary to have 64-bit representations of anything. So a typical graphics card for gaming, even though it costs $1,500, the fanciest one, It has a lot of cores, but most of those cores are 16 and 32-bit cores, because that's what it's for gaming. So in that sense, it makes a difference. If you use a graphics card that's designed for games to do computation, say to run a neural network or face recognition, right? You don't want to do 64-bit computation, because that graphics card for games have very few 64-bit cores. But if you do 32-bit or 16-bit computation on it, it's quite good. Those, Titan card for games would work extremely well for neural network computation in 32 and 16-bit, because they have a lot of cores for that. Okay.
Thank you.
So that's 41. So I want to also do the exercise of going backwards from this value, right? If I go from here, 1 corresponds to 2 to the 0, right? 2, 0 to the 1, this 0 to 2 to the 2, 1 to the 3, so on and so forth, and this is a simple addition. Now, there's another procedure to get from 41 to that end. In here, there's only one way to do it, which is take the ones and multiply with the powers of 2 and get the answer. But I want to show you another way, which is I'm going to divide 41 by 2. I don't know what the right division sign is. I'm just going to say that. And I'm going to call this integer division. Integer division, I don't mean the exact division. If I do exact, 41 divided by 2 would be what? Exact. 20.5. I don't mean that. I mean the integer which gives me a quotient, right? And a remainder. So if I do this division, what do I get with the Q and R? It's 20 times 2 plus 1, right? So just a reminder of integer division, which is going to be a big deal for us. This is the remainder. This is the quotient, right? And there's some rules of those quotients and remainder. Like if I divide by 2, like in this case, what are the possible remainders?
0 and 1.
What if I divide by 8?
Between 0 and 7.
So see how that lines up quite nicely with these digits here? When you divide by 7, the possible remainders are exactly 0 to 6, which are also the possible digits in base 7. When I divide by 4, the remainders are 0 to 3, which happens to be exactly the digits in base 4. That's not a coincidence. The way system of numeration works in certain bases and the way integer division works is actually the same way. It's just written in different words. So think about that by next time, Tuesday. Why is it that the digits in a base, like base 4, are exactly the remainders of integer division with 4? So even further, we're going to do this in more details. What's up with the quotient, what's up the remainder, and all that. This remainder here is something in base 2. This little one here corresponds to a certain digit in base 2. Which digit is that?
The units digit.
Which is?
The times 2 to the 0.
On the right,
yeah,
right?
All right.
So this is the least significant digit in base 2, aka most right, on the right side, this one here. Now, how do I move on to the next digit? So I've done that, I've got the last digit. Well, I think most of you know, right? If I tell you that rule, you'll say, oh, I've heard that before. I look at 41, the remainder at 2, which is 1, obviously, this number is not a multiple of 2. This fact that this is an odd number, it does not divide by 2, tells you what? In base 2, the last digit is going to be 1. Because odd numbers in base 2 must have the last digit 1. How about the next digit? Now that I've dealt with that 1, so I've got it, what do I do next?
Divide by the 20 by 2.
Very good. So now I take this 20, that's from here, and I divide the same integer division by 2, what do I get?
10 times 2 plus 0.
10 times 2 plus 0. Who is this 0?
The next bit.
That's the next digit. What happens next?
10 divided
10 divided by 2 is what?
5
5 times 2 plus
0.
0. 0 is the next digit. Next,
5 divided by 2.
what do I get?
2 times 2 plus 1.
So this 1 is this digit. Next,
2 divided by 2.
so this 5 is from here and this 2 is from here. This divided by 2 is what?
1 times 2 plus 0.
So this 0 is where? Here, right? And last one, this 1, the moment I get the 1, there's no point doing that. If I keep the division, I'm gonna get 0 times 2 plus 1, and so on and so forth. So I can go with 1 more time. 0 times 3 plus 1, that's the last digit. And now that I got 0, I stop. So I think there are 2 procedures that will get you the same result. Obviously, they are very related.
2 divided by 2 equals 1 times 2.
I mean,
Just 1, isn't it?
no, I think it's 1 times 2. Sorry. The 2 is always here because I divide by it, right? So 1 times 2 is 2, plus 0 is 2, right?
But 2 divided by
2 divided by
2
2
divided by 2 is equal to 1.
Yeah, so maybe I didn't write it very formally. 5 divided by 2. I'm just saying that this 2 is not part of this 2 is the divider that I'm dividing with. So 2 times 2 plus 1 gives me 5, right? 5 times 2 plus 0 gives me 10. So maybe this is not right to put it equal, put it more like this is what happens when you divide that. He's right. Formally, when you say 2 divided by 2, if you put an equal sign mathematically, the answer is 1. It's not 1 times 2. That's a good point. We're a little bit informal here, computer science, right? And we say, when I use this division, I get a quotient, right? Which is this guy, and the remainder. So these 2, it's fixed in stone because these 2 is what I'm doing the division with. It's the actual answer plus the remainder. Okay. Are we not confused about that? This is the integer division that you are familiar with. There's nothing new here. What I want to say is, when you transform a number from base 10 to base 2, there's 2 procedural ways of doing it. I like this one because in my mind, it's easier to get the powers of 2 out of a number. If you tell me, 387, what's the closest power of 2 that fits in it? 256. How about 1149?
1100.
Huh? 1024. I like to think that way. What's the biggest power of 2 that fits in that number? So I could get it out. And in base 2, you don't have to worry about the digits. If it fits, the digit is 1. If it doesn't fit, the digit is 0. But an equally good way is to do repeated integer division. To say, okay, divide, get this reminder, that's the bit. Now forget about the reminder, just keep the quotient, keep dividing, and then you get the following bits. Those are equivalent procedures. Gives the same answer. Let's do another one. I have here an example. 105. Actually, let me try not to write in there because it's hard to see. Are we recording on the camera?
Yep.
Yeah.
39, 20.
So how about 105? Yeah. Do we have until 11:30?
Wait, if you write in like the dark spot, it can't see it on camera. So if
Like
you
the
bring it
shadow.
down.
Because it's too shallow.
Yeah,
right?
yeah.
Oh, cool. Sorry.
Whoever designed those lights here thought more like a spectacle than an actual class.
Definitely.
This would be great for a play theater or some dancing. Not ideal for a whiteboard. 105. I'll do it my way first, take the powers out, and then we'll do the division to make sure we get the same thing. So what's the biggest power that fits in 105? 64, which is 2 to the 6. How many times it fits? In bottom page 2, it only fits once. You can't fit more than once because it would fit twice. That would not be the biggest power, right? If 64 would fit twice in my number, that would be an incorrect way of doing it. The right way would be to get what? 128, right? So if I take 64 out, how about 32? Is that also fitting in 105?
Yeah.
All right. Plus, once I get 64, sorry, you guys can't see. 64, 32, how much is that total? 96. How much I have left?
9.
9. So 2 to the 4 fits? No. What fits in 9?
8.
8. So that's 2 to the 3. And then, of course, the remainder now, after I take the 8 out of 9, I get what? 1. So 2 to the 2 and 2 to the 1 will not fit. So I get a 1 times 2 to the 0. So this is no 16, I get an 8, no 4th, no 2s, I get a 1. So again, 64 plus 32, 96, plus 8, 104, plus 1. So now as a representation in base 2, I do that bit 1, 1, then I get a 0, then I get a 1, then I get 2 zeros, and then I get a 1. Make sure I got it right. 1, 1, 0, 1, 0, 0, 1. These are 7 bits. And I could choose on how many bits do I actually want to write it down. If I use a computer and I use it, say, on 8 bits, I add the 0 in advance to complete the 8 bits. If I do 32 bits, how many zeros would I have to add? Other than this one.
Too many.
About 24, right? Because if I want to get to 32 bits, I need to add all the zeros to 32. Okay? How about we do it now the other way, which is the integer division. If I am to divide this by 2, what do I get? 52 times 2 plus 1. So that is the last bit. Least significant, or the unit bit, or most to the right. Last bit. Right? Then I get the 52, divide by 2, I get what?
26 times 2 plus 0.
That's the second. Second to last bit. Next, 26 at 2. I think, as he pointed out, we shouldn't put the equal sign because that's not correct mathematically. If you say 26 divided by 2 is what? 13 here times 2 plus 0. That's the third to last. So you can see how these bits are coming out from the right this way, 1, 0, 0. Next up, 13 divided by 2 will result in 6 times 2 plus 1. That's the next bit. 6 divided by 2 is what? 3 times 2 plus 0. 3 is going to be what? 1 times 2 plus 1. And then 1 is going to be 0 times 2 plus 1. And then I got a 0 here, so I stop. So now how do we read this number in binary? Where do we start reading? This is the most significant. So that's to the left. So if I read this number 1, 1, 0, 1, 0, 0, 1, the same as this number. 1, 1, 0, 1, 0, 0, 1. And I could choose to add a bunch of zeros if I want to. That depends on how do I store my numbers. Whether it's 8 bits, 16 bits, 24. Some people use even non-multiples of 8, you know, represent numbers from 20 bits maybe. I have an application that does that. That's fine. But you have to know how many bits you want to use when you do those things. Okay? So are we good with this? Hands up. Who's following me? There's going to be a lot of this in the next 2 weeks. The first 2 weeks of the course. Transform. And, you know, most of mistakes, to be honest, there's no one single student I've seen that doesn't know how to do this. But about 20% of the students make mistakes, which are simple manipulation, algebraic mistakes on those quizzes and simple exercises. It's not like you guys don't know, but you have to be patient. I know it sounds trivial, I know it sounds, I get it like that, and you miss a zero or something, and then it's the wrong answer. So take your time to do it right. Maybe one more example. This, and we'll see if you guys can see or not. I don't know. Maybe that chair is not. Huh. Dancing time. I have here 83, base 10 of course. Not in the shadow, I have to remember that. So if I do it without integer division, what do I get? 64 plus 16 plus 2 plus 1. Now I have to be careful with the bits. This is 2 to the 6, right? So it gets a 1 here, but this is what?
2 to the 4.
2 to the 4. So it gets a 1 here, but I need a 0 representing
5.
2 to the 5. If we just put 1, 1, that'd be incorrect because you have to put a 0 for 2 to the 5th, right? What am I missing here? This is 2 to the 1, so that's a 1. But from 2 to 4 to 2 to the 1, how many zeros I need in between?
2.
1 for 2 to the 2, and 1 for 2 to the
3.
So I need 2 zeros in here. Because from 2 to the 1 to 2 to the 4, I'm missing 2 powers, which is the 4 and the 8, or 2 to the 2 and 2 to the 3. And then, how about this? This is an immediate bit, right? I don't need anything in between, this is 2 to the 0. So I've got this representation, 1, 0, 1, 0, 0, 1, 1. Is that correct? Yep. If I do the integer division fast version, I say 83 is what? 2 to, what multiplies to 2 to give me 83?
41.
41 times 2 plus
1.
1. Let's keep going. 41 is what?
20 times 2 plus 1.
What?
1.
Yeah, 20. 20 times 2 plus 1.
20 times 2 plus 1. I put a parenthesis here because that's just 41 now. Then I have to keep correctly times 2 plus 1. This is coming from the previous division. And now I keep going with the 20, which is what? 10 times 2 plus 0. Right? That's the 20. And I have to say times 2 plus 1. That's this parenthesis now. And then I still have a times 2 plus 1. Correct?
Mm-hmm.
So if I keep going this way, this 10 in here, what is this?
5.
5 times 2 plus 0. So that's just the 10. I'm doing now times 2 plus 0. That's now this parenthesis. Times 2 plus 1 is this parenthesis. And times 2 plus 1 is the whole thing. So we have to check those parentheses. Open, open, open. Closed. This closed matches with who? With the last one open. This second close matches with the second open, and this close matches with the first open. Parentheses have to match that way. Many editors for writing programs will match your ending bracket with the beginning bracket to give you a visual sense of matching parentheses. And if I keep going here, this 5 is 2 times 2 plus 1, that's just the 5. So I do plus 0, that's this parenthesis, and then I do times 2 plus 0, that's this parenthesis, times 2 plus 1, that's this parenthesis. So now I have open, 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 close, 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 close. One more time. These two, which is my quotient here, it's really what?
1 times 2 plus 0.
1 times 2 plus
0.
0. And that's just the 2. So I have to multiply times 2 plus 1, close, plus 0, close, times 2. I guess I'm missing a little 2 in here. This is times 2 plus 0. Times 2 plus 1, times 2 plus 1. So I have 1, 2, 3, 4, 5. Times 2 plus 0, I guess we're missing something. This 2 is 1 times 2 plus 0, and it's times, how does this go?
You're missing the second 2 times the second 0.
This?
That one, yeah.
So 1 times 2 plus 0 times 2 plus 1, that's here, times 2 plus 0, is that right?
No. Yeah.
This is that, this is that, this is that, and that, right? So now the bits, there's one more step here, but the bits you can tell. This is the bit here, this is the bit, 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 and so on and so forth. And those bits are, this is just the integer division, written in a more dense way, perhaps harder to execute on paper. You can get lost easier that way, just like I did in there. I think doing it this way, it's much more, maybe it takes more space, but you get more clear where you are. For me personally, so either way it's good. If I tell you transform a number base 2, whatever procedure you come up with, that's fine. But to me, in my head, this one with the powers is the easiest thing to do. Maybe because I know the powers of 2 up to like 4,000 or something, it's just easier to do it that way. Okay, so now, how addition, remember where we started with addition? How addition works in base 2? No surprises, it works the same way as in base 10. So if I have here 22, it's one of the numbers we did, so we can say here addition. 22 is 1, 0, 1, 1, 0. Is that true? 16 plus 4 plus 2. How about 21? That would be 1, 0, 1, 0, 1. If I add those two, of course I get 43. I should get the same value here, just represented of course in binary. So how addition works? 1 plus 0? 1. 0 plus 1? 1. 1 plus 1?
1.
1 plus 1 is 2. Really remember how we thought about here? We say 9 oranges plus 2 oranges as a quantity, it's 11 oranges. 1 plum plus another plum is 2 plums. But 2 in base 2 is not a 2. You can't write a 2. 2 in base 2 is what? It's 1, 0. Right? So if I am to write 1, 0 here, it's like in base 10. I have to write a 0 here I can't write 1 0 in one spot, nor do I can write a 2. 2 is not a valid digit, but I keep a carry bit, just like in base 10. The principle is the same, is because of this. When I get 2 oranges, they really take me to the next power. That is 1 digit to the left. So I have this carry now, carry 0 0, what do I have? 1 and no carry, and then 1 plus 1 again, it's a 1 plus the carry bit. Is that true? Is that 43?
Yeah.
This is 32. This is 8, right? 240. Simple addition. You cannot believe how many mistakes in additions in base 2 I've seen in my life. It's so easy, yet I would say 40% of the people who attempt calculations like additions in base 2, 40% of calculations tend to be wrong. And when you get to subtractions, that's even higher, the percentage. The subtraction is really funny in base 2. We'll get to that next week. Again, like I said, I know you get it. I'm convinced. You cannot even convince me otherwise. If you say you're not getting, I won't believe you. Okay? But you have to take the time to do it right. Doesn't matter if you spend 1 more minute on it or you know, check it again. Even me, which I've done 30 years of mathematics, once I do this, I look at those bits and say, let's add them really quick to make sure I got the answer. As in 32 plus 8 plus 3, just to make sure, right? So you should do that. You should not leave the result just like that. It has to work. It's true, mathematics has to work. Checking it might reveal some mistakes. But another example here. With addition, we'll take about, we can do a just for fun subtraction. So we'll say, how about 26? That's a plus here because we did an addition. 26 minus 7. I won't explain how this works until next week, but we can verify the result. 26 is 1, 1, 0, 1, 0, is that true?
Yeah.
16 plus 8, 24 plus the 2 is 26. 7 is what? Of course, it's minus, so that's the part that's not clear how it works. It'll be clear next week. But 7, we know what 7 is, right? 0, 0, 1, 1, 1, right? So this is 1, 2, 4, that's a 7, and I stick the minus in front of it. This minus is going to be a complication for computers. I mean, we can do it because we understand negative numbers, but computers have to have a way to represent the negative numbers. We humans, we put a minus in front of it. Computers have no minus. There ain't no minus. It's just a bunch of memory locations. So they got to do something to represent that minus. Right? Computers do operations fine with negative numbers. We're going to have to deal with that. That's what we're going to spend our time next week on. So here's the result. If I say 1, 0, 0, let's align it a little bit. 1, 0, 0, 1, 1. I get this result. I can verify the result easily. I could say, well, for this to be correct, this plus this should give me that, right? The answer in here is what?
19.
19. So it's 19 because 19 plus 7 gives me 26. 1 plus 1? 0 plus the carry. 1 plus 1 plus the carry. 1 plus the carry. Right? Again, let me do this slower. 1 plus 1. I'm trying to add those numbers to verify that I get this result here.
Good.
1 plus 1, 0, and the carry. Carry plus 1 is 1 and the carry. Carry plus 0 plus 1 is 0 and the carry. Carry plus 0 is 1 and no carry. And then 1 plus 0 is 1. So I know this is correct because if I add them back, I get the answer. But I didn't show you a procedure of how to get this value, right? I just say, if that's the answer, I could verify it. Verifying something is not the same as obtaining it. Usually verification is a much easier process than obtaining the result. Right? If somebody gives you an answer, sometimes verifying the answer is very easy, but obtaining it, it's hard. Actually, that's a fundamental computer science problem. Many problems, like cryptography, for example, relies on that fact. Verifying an answer, it's very easy, but obtaining the answer, it's very hard. All cryptography in the world today relies on factorization, breaking a number into factors, you know, as in who is 143? Is 11 times 13. It turns out, mathematicians figured this over centuries. Verifying, if somebody gives you 11 and 13, verifying that their product is 143, it's very easy, very fast, right? Computers will multiply even big numbers. We're talking about numbers that have many, many, many bits, thousands of bits. Multiplying two numbers to verify the answer, easy. If I give you the number and I'm asking you, find me the factors, very hard. If you find an algorithm to obtain easily the factors of a number, you break cryptography to everybody in the world. All the banks, all the passwords and all that, because all cryptography and security relies on this mathematical fact. Multiplying numbers to verify the product, easy. Getting a number into factors, very hard. Okay? Same thing in here. I didn't show you how to get it, but it's easy to verify. Of course, I could get it in base 10. I say, well, I don't know how to do it in base 2, so I do 26 minus 7, 19, and then I write down 19. That's a procedure, but that's not what we want. We want to figure out how to do it in base 2. So let me show you a little bit more complicated example. Actually, before we do, I still haven't learned how to use these boards. Before you do, we're going to move to that example in a minute. I want to talk about bitwise shifts operation. For now, I'll talk about this informally, and at some point, I'll show you something more formal on the computer. Because computers represent numbers that way, this is the number 105. And because this integer division gives the bits, people have thought, hey, wait a minute, in a computer memory, now thinking about engineering, what happens, so this number you can see in here, it's on 8 bits, right? I choose my representation to be 8 bits. Suppose that's fixed, as in there is no way to write the 9th bit on it. It's always 8 bits. What happens if I take all these bits and move them to the right or to the left? But I want to think today in terms of engineering. Physically, I want you to imagine I have 8 slots. That's my memory, right? 8 positions. What happens if I take those bits and move them one to that side or to that side? So let's do that thinking. Here's my slots, right? There's 8 of them. So I have 8 here, right? And I have my representation 0, 1, 1, 0, 1, 0, 0, 1. And those slots are fixed. This is the physical memory. When I say shift, you can shift the memory locations. Those are fixed in silicon. What you can shift is the bits on these locations. You can say, move all the bits to the left, or move all the bits to the right. So if I move, say, all the bits, move all bits to right by 1 position. If I take everybody, move to the right. What's going to happen in my array here? Which is, again, fixed in silicon. That's my memory. Memory doesn't move anywhere. It stays there. Just the bits move. This one here to the right, what happened to it?
Gone. Gone.
It's gone. It's out of, even though there's more memory, like my memory has more slots, the way it works, if you say 8 bits, you can't access that next bit. That's, your iTunes playing songs or whatever. Computers, especially modern kernel, modern operating systems, don't allow you to go over some space of memory that you don't allocate to your program or to your thread. So this slot, even though there is a memory slot here in my chip, my RAM, it's not available to my program because it's allocated to something else. This, by the way, was a great way to hack into computer systems until about 10 years ago. Figuring out, trying to guess what's on this part of the memory, maybe that's where the password is or something, writing certain things just to access those bits. The kernel didn't have that memory protection, the operating system. It allows writing here. That's how people got in systems like hackers. There's a very well-known called overflow method to be able to access parts of memory that you are not supposed to access, guess what's on there, write the right bits to guess, and hackers can guess because they can do a million guesses. It's not a problem if they get some of them wrong. Now they fix that. Kernels now don't allow you to write in parts of memories you don't control, so you can't do that anymore. All operating system, Linux, Mac, Windows, don't allow you to do that anymore. Anyway, what happens if I move to the right? This one is gone. So what do I get? 0, right? 0, 1, 0, 1, 1, right? Those are the 2 ones here. This 0 moves in here, right? What about here?
0.
When I move things and I leave an empty space, empty means 0. That's how memory works. This is a very fast operation. Computers can do this extremely fast with what's something called masks. They don't have to literally move every bit. So that's the good part about it. That can happen very, very fast. Well, so that's a shift to the right. And the operation, I think it's marked with like some sign like that. But what happened in reality with the number, with the quantity? This was what? 105. When I shifted to the right, that's what happened in memory. But what happened in mathematics conceptually? What did I do?
Divided by 2 and truncated.
Right. So what did I get when in here? When did I divide by 2 and truncate? This is the division by 2, and truncation means ignore this bit. This is the bit that went out. So whether it's 1 or 0, it wouldn't matter because now it's out. So the end result after I divide by 2 and truncate, aka shift to the right, should be what? 52. It's 52, this guy? What is it?
30.
32.
32.
16.
32 plus 16?
48.
48 plus
4.
52? Jackpot. What happens if I shift again to the right? How is my 8 bits going to look like? Again, what it's gone, and what is new, it's going to be 0. So in here I'm going to have 0, 0, 0, right? Because I'm adding the 0 in the front. This is only 1. 0, right? 2 ones. This value should be the same. Divide by 2 and truncate. This operation shift, it's exactly that. Divide by 2 and truncate. So that should be who? 26? If you think about, even as a power of 2 representation, this makes sense. Why? 105 was what? We have it right here. 2 to the 6 plus 2 to the 5th plus 2 to the 4, right? Plus 2 to the 3. No, not 2 to the 4. Let me write the 9 so you guys can see. So what happened is 105 plus 2 to the 6 plus 2 to the 5 plus 2 to the 3 plus 2 to the 0. I'm talking now conceptually, it has nothing to do with base 2. Shifting to the right means what? Every single bit that was bit at 2 to the 6, when I shift to the right, is now in what position? 2 to the 5, right? And this bit that was in position 2 to the 3, when I move it to the right, becomes 2 to the 2. So every single bit, when I do the shift, I can immediately mechanically tell what the number is going to be. 2 to the 6 becomes 2 to the 5. 2 to the 5 becomes 2 to the 4. 2 to the 3 becomes 2 to the 2. And 2 to the 0, which is 1, disappears. So mechanically speaking, shifting to the right means moving every single bit from its position to the one that's lower power, which mathematically means divide by 2, right? Because 2 to the 6 by 2 is to the 5, to the 5 by 2 is 2 to the 4, 2 to the 3 by 2 is to the 2. And this bit is going to get ignored, getting out. Doesn't matter if it's 1 or 0, it's going to be 2. So those things, integer division, shifting to the right, decreasing the powers here, every power gets 1 lower, or taking the bits literally and push them out by 1 position, are the same integer by 2 division. Who's with me? Hands up. This would be a great time to ask a question. Yes?
So I'm guessing that also works for like base 10, so you just shift it down by power of 10.
That's a great question that I don't want to answer. That's a great exercise. What happens in base 10 when I shift? By 10, right? Because if I have a digit, say digit 3 in base 10, it's 3 times 2 to the 5, 10 to the 5, right? I have this digit 3. When I shift one spot, this is still going to be a 3, but the power is going to be 10 to the 4. Now, that's true if you think of shifting as in shifting the number. For example, 3, 2, 1, 5, 8. This 3 is in position 0 to the 5th, right? When I 8, 9. When I shift this to the right by 1, I get what in base 10? 0, 3, 2, 1, 5, 8. Conceptually, however, shifting cannot work in base 10 for a computer. Maybe you can take a bunch of digits and move them to the right by hand, but computers will not be able to move to the right in base 10 because they do this operation shifting with the bits they have already in memory. That's why it works so great in base 2. In base 2, I can just take whatever physical representation I have in memory and move everyone to the right. In base 10, I can do it by hand, but this operation is not an easy operation for the computer. It's easier to just divide by 10. However, I can do shifting in base 4 easily. How do I shift a bunch of bits one position in base 4? Shift them 2 positions. If I want to repeat the operation, that's something for you to think about. In base 10, it's hard to implement because there is no way to take the bits representation of this number and move them right or left and get anything useful. But if I want to do it in base 4, I want to do a shift in base 4 because 1 bit in base 4 is 2 bits in base 2. We're going to get to that next week. I can do this operation by, if I want to do a shift in base 4, I just move it 2 positions in base 2. And that's equivalent to the shift in base 4. How about base 8? 3 positions. So shifting is possible in a computer easily in base 4 or 8 or hexadecimal, which is 16, because it maps easily to operations in base 2, which are the natural representation, the physical representation. But in other bases, shifting is not so easy. I can do it to the left too. Right? What happens if I take this 105 and I move it to the left? That is that way. I take this bit, I still have 8 bits. Remember, that's very important. I decide to have 8 bits, I have to stick with 8 bits. I cannot change my representation. Well, I literally take the bits, move them, right? So what's going to happen here? 0, because this comes from outside. It doesn't matter what was in this iTunes memory playing songs. Whatever bit was here, that's not the one that's moving in. When I move something in and I control my bits, 0 is coming in. And then I have those bits. 1 from here moves in here. 0 moves here. 0 moves here. 1 moves here. 0 moves here. This is a 1. This is a 1. What happened to this bit? Gone. I can't use a 9th bit. Gone in this case maybe doesn't matter because 0 is not affecting the quantity. But in any case, if I have 8 bits, I can't move things out. In this case, I couldn't go to the right. In this case, I couldn't go to the left. So what is this number now? Repeating this argument, I take back the 2 to the 105, and I say, what happens to move to the left? 2 to the 6 becomes 2 to the 7. 2 to the 5th becomes 2 to the 6. 2 to the 3 becomes 2 to the 4. And 2 to the 0 becomes
2 to the 1.
2 to the 1. Effectively, I multiplied by 2. Every bit is now representing double the quantity. It was representing 2 to the 5th. Now the same bit represents double 2 to the 6th. So what should be the value if this is 105? 105 becomes what? 210. Moving to the left is multiplying by 2. Well, is there any case when moving to the left is not really multiplying by 2?
Anytime the most significant bit is a 1.
Right. If this would be a 1 here, the value would not be 105. The value would be a much bigger number. This 1 stands for what power of 2?
7.
Which is?
128.
128. So let's do that. If this is a 1, this in here, it's easy for me to erase the board and write on top of it. Not so easy for you to write the whole thing again. I know. A little bit annoying here. 105 plus 127 is?
230.
105 plus 127.
Oh.
105 plus 127. 232, right? If I shift it to the right, I still get 210. Because this bit here, that's the 127, went out. This bit doesn't count anymore. Hands up who's following me. We need to explain this again. On 105, things were clear. This was a 0. Everything moved to the left. Every bit was doubled. This 0 went out, but it doesn't matter. So the number became 210. However, if this bit is 1 and the number will be much bigger, it will be 232. When I move everything to the left, I get the same answer because this 1 goes out. What? 233, correct. 128 plus 105.
Yes.
But the point stands that this 1 going out means it's gone, and then only these bits matter, which means I get the same answer.
The camera's about to die. It's at like 1 minute left.
Should I stop recording? Or?
No, you should not. Somewhere in there must be a plug.
Is there like outlets down here?
You have to.
You guys find a plug somewhere?
Yeah, I can see a plug right this.
Okay.
This is like
So
emergency
you plug it in,
operation.
and I think it's on the right side. Sorry.
What is the outlet?
No,
That's it. It could be.
I think somewhere on the right side.
Can I just want to rewatch this lecture?
You found
Oh
it?
yeah, we're good.
Alright, we're good.
Teamwork.
We don't want to stop recording. Yes.
Is it ever beneficial to wrap bits in the shift register?
What?
Is it ever beneficial to wrap bits, say from the most significant to the least significant spot when you're shifting?
I'm not sure I understand the
So, like,
question.
move it so it doesn't get lost. Like it just
So I don't get it lost.
You like move it to the other side, the empty space that you open up.
In here.
Yeah.
I mean, you mean circular, like take this bit and put it on the other side?
Yeah, is it ever beneficial to do that? That's what I'm asking.
I don't know if it's efficient, but it's not the result we want.
Yeah.
That would not be a multiplication by 2, right?
Yeah.
So you could imagine like a cylinder. I don't think it's efficient, but you could imagine an operation that takes this lost bit and puts it in that space. I think he thinks of like saving it somehow, not lose it. But that's not, I think the main point is to get the right answer. To get the multiplication to work, we have this bit to be here for the answer to be double that.
And if you're doing 2's complement numbers and you want to divide by 2, then it's useful to preserve the leftmost bit. So if the leftmost bit is a 1 and you shift right, then you keep the 1 in the left. Copy it for negative numbers.
Well, that's too hard for everybody to follow. Next week on Tuesday, first thing is 2 complement. So we'll see how that bit goes. The only thing we should follow for now is that when we talk about negative numbers, the first bit is the sign. So then we have to deal with that first bit. If we do weird operations like this and we lose the sign, you know, things are going to break really bad. But the general question of losing bits is not just shifting to left and right. It has to do with overflowing operations. When I, for example, multiply 2 numbers on 8 bits, but the quantity is too big to fit in 8 bits. So I'm not getting the product, right? You had a question?
Yeah. So there's a rule for when we shift it to the right and when we shift it to the left, the first number is 0. They're divided by 2 and truncating it. Is there one? Then it's 1. Like when the leftmost number.
It's 1.
Yeah.
So when we shift, I want to be very clear. When we shift, think about it as a mechanical operation. This bit gets lost, no matter what.
Right.
Now what happens as a quantity, so if it's 0, it gets multiplied by 2. If it's not 0, it's not multiplied by 2. It's multiplied by 2, but only that part without the bit. So we'll have to, I said before, I talked about this informally. I wanted to show you mechanically the shifting operation. If you use it in your program, for example, if you shift things, you have to be very aware of what you're doing, because you may lose bits. But the intention of shift is to lose bits. So you should use shift operations in a programming language when you specifically want to get rid of that last bit. You don't care. Like in here. If I want to do integer division, I just shift to the right and I get the quotient because I don't care maybe about the remainder. I only care about that. So we'll talk about more about shifting operations more formally, but for now think of it as move to the left, to the right, and lose that bit that's at the end. Okay, I have one more example here, and then I want to connect my computer to show you something online. So I have this example here, 177 and 147. If I add them up, base 10, that's 4, 2, 3, is that correct? Yeah. So 177 in base 2 is what? I'm going to use my favorite method, getting the powers of 2 out of the number. So what's the biggest power that fits in? That's 2 to the 7. What's the next one that fits in?
5.
64 fits in?
No.
No. So it's a 32, right? Let's actually write it down for you to be able to read these notes later on. Easier. 32 plus what else fits in it? 128 plus 32 is 160. 177. I have 17. 17 will be what? 16 plus 1. Okay? So that in binary is the bit of 128 right here. Then I get what? 0 for who? 64, because it's missing. 32 is a 1. 16 is a 1. And then from 16 to 1, how many things I missed? 3 zeros. Right? This is corresponding to 8, 4, and 2 powers. How about 147? It's 128 plus 16 plus 2 plus 1, is that right? So what is this? 128 is the same one, of course. 0 for 64, 0 for 32, 1 for 16, 0, 0 for 8 and 4. Then this 2 is this bit, and this 1 is this bit. So now if I add them in base 2, what do I get? 1 plus 1? 0 and the carry. 1 plus 0 plus the carry, 0 and the carry. 0 plus 0 plus the carry, 1 and no carry. 0 plus 0, 0. 1 plus 1, 0 and the carry. Carry plus 1 plus 0, 0 and the carry. Carry plus 0 plus 0, 1. 1 plus 1, 0 and the carry. Now, how many bits I have here? 0, 0, 1, 0, 0, 0, 1, 0, 1. If this would be an operation on 8 bits, I wouldn't have this space for this one. If my space is 8 bits, when I do this addition, that's lost. So very important observation. If this is on 8 bits, that means the 1 times what power of 2 would this be here?
256.
Which is 2 to the
8.
8. This bit is called overflow. Again, that relates to how people attack the memory on the left side. It used to be the case that you can overflow and write on some random piece of memory, but modern operating systems prevent processes to write on memory that they don't control. They have a table, and every time you try to write there, it says, whoops, you're not allowed. If this is on, say, 16 bits, that's 1 times 2 to the 8. That bit in there, the leftmost bit, is fine. So if this would be an operation on more bits, if I have this bit for myself, that's fine. I could use 9 bits and maybe fill them with zeros if I want all the way to 16. If I have that location for me, I could use that bit. And in this case, I think that would be a correct operation, right? Is 324 exactly this value?
Yeah.
It is, right? Because 324 is who? 256
64.
plus 64 plus 4, which is that value over there. 256 plus 64 plus 4. Again, if I were to do this on 8 bits, that would be a problem because this bit won't fit. Okay? For this example, because I have it in the notes, I would also want to do it in base 4. The same exact operation. So if I'm to write 177 in base 4, what's the biggest power of 4 that fits in 177? Not power of 2, power of 4.
64.
64. In base 4 is not just fit or don't fit.
Twice.
There's digits. Digits are
1, 2,
1,
0, 1, 2,
0, 1, 2, 3. So the question is how many 64s fit in there?
2.
2 of them. Plus, what's the next power of 4 that fits in? 16. How many times it fits? Well, 2 times 64 is 128. Out of 120 on 177 is what?
49.
49. And then how many 16 fit in 49? 3 of them. Those are the digits, of course, in base 4. So what's left? 1, which is 16 to the 0, 1 on it. Right? So the representation in base 4 is 2.
Yeah, you
4 to the 0. 4 to the 0.
4. This is 4 to the 2, and this is 4 to the 3. It's base 4, so we deal in powers of 4. What's the number? There's a 0 here corresponding to what power of 4?
1. First power.
There's a power of 4 missing, so that's a 0 plus 1. Okay? So this number in base 4 is 177 in base 10. How about the other one? 147 in base 10 is, what's the biggest power of 4 that fits? I think it's still 2 times 64. But now things change. How many 16s fit in there? 1. And then what's left? 3. So 3 is what? 3 times 4 to the 0. 3 is an accepted bit in base 4. Right? So this value would be 2103 base 4. If I add those things in base 4, what do I get? Base 4. 3 plus 1 is 4, but 4 is not allowed. 4 is really
0.
in the next bit. So I have a 0 and the carry. 4 really is 1 0 in base 4. 0 plus carry?
1.
1. 1 plus 3? 4, again, which is a 0 and the carry. 2 plus 2 plus the carry?
1.
It's 5, which in base 4 is really 1 and the carry. 1, 1 is 5 in base 4, right? So I've got this value here, base 4, which we should verify. It's really 324, which is the sum. 324 would be, what's the biggest power of 4 that fits in? 256. 1 plus, what other power of 4 fits in? 64. 1 plus 4, right? So that you can see the bits 1 at 256, which is, by the way, 4 to the 4. This is 4 to the 3, and this is 4 to the 1. So I have a bit on 4 to the 4 right here, another bit on 4 to the 3, a missing power which is 4. This 0 is 4. What power? 4 to the 2. You can see there's no 4 to the 2. And I have this 1 for 4 to the 1 and 0 because I have no units. Yes?
Why is it when you add the 2's together and the carrot of the 1, you put a 1 there?
2 plus 1 is 5. In base 4, that's a 1 and a carry.
Why wouldn't you carry like a 2 over the 0?
But 5 is not 2 and a 0, right?
Then why is it that when we do 4, we have a 0?
Here?
Yeah.
So 1 plus 3 is 4. 4 is really 1, 0 in base 4, right? That's why I put the 0 and I keep the 1.
Oh, okay.
But 5 as a quantity is really 1, 1 in base 4. So I put the 1 and I keep the carry for the other side. It's like in base 10. In base 10, if we have, say, 8 plus 7, we get 15. So what do we do in base 10? We put the 5 and we keep the carry as a 1, right? We don't put a 0.
Yeah.
Dancing time again. We're really going to call these people and say, fix this, please. Maybe there is a button here that you can press and stays on. And, right. Okay? So are we good with this? Yeah. We do a lot of base 2, but the principle of additions and representation is the same in all bases. Now, I want to show you something. I'm going to turn on this projector here. Now would be a good time to
Wait, do you want us to like move this up so you can see it?
no, let's see how it goes. I don't even know where this is going to project. So I think I'm going to turn the lights off a little bit. Okay, not bad. A little bit high, but not bad. What I have here, the first thing I want to show you is the trick with the cards. You guys all remember the trick with the cards? Now we're gonna completely figure out how it works. But before I go to those cards, I want to show it to you in base 10. Those are a bunch of numbers, and they're a bunch of cards, just like you had yesterday or Wednesday. Every card has to do with a digit in base 10. The numbers are from, I think, 1 to 350. So there's 3 digits, right? I want to have a card for everybody who has this digit, say 2. What are the numbers that have this digit 2? Everything that has something, something 2, right? That card, I think it's somewhere in here. The card that has everything ending in 2. It's supposed to be. Is it? Is it this one?
Yeah.
That card has all the numbers that end in 2. Right? How about if I want the card that has all the middle digits being 6? As in something, 6 something. Anything. Where is that card? That has all the things that have a 6. Did I pass it?
Did you type it?
There.
I did.
I pass it again. There you go. That's the card that has all numbers have the middle digit 6, right? So for me, there are 24 cards. Let's see, what is this second card here? What is this? It's all the numbers that have the first digit 1. How about this card over here? All the numbers that have middle digit 0, right? So how would I do this trick with decimal cards? I do the same thing. Think of a number, give me the cards that contain the number. You're going to give me a bunch of cards back, right? Now, one of these cards will tell me what is this digit. I look at it, I see all the numbers that have a 5, no 5 because it's 2. I say, this is the card that has the 100 digits 2, so you must have a number that starts with 2. Another card that you give me will be something that has all the digits, middle digit 6, and maybe this is a 1. So what cards, if you think of the number 261, what are the cards that you're going to return back to me?
200.
Will be the one that has all the beginning with 2, will be this one, right? 261 is in here. Then you're going to give me back all the ones that have 6 in the middle. You're going to give me this one. And you're also going to give me the one that have the last bit 1. So once I look at those cards, I see that each card is a digit. You're going to give me back 3 cards, and I can tell you return the 2 as 100, 6 as a tens, and 1 as the unit digit. So the number must be 261. Procedurally, I could just add up the corner numbers because 1 appears as the corner number there. 6 would probably be a 60 here. That's like the card that. And then the 2 will be on that card that has all the cards with 2 will probably be the first corner number, 200. So when I do 200 plus 60 plus 1, I get the value.
If you pick the number 1, I saw 2 cards that have 1 in the first top left corner. So if you pick the number 1 and try adding them up to get 2. Top has 1. And then
Yeah, it doesn't start with 0. It doesn't start with 0.
Right. The problem, I think, is in here, they are not sorted properly. The card is correct, but what is this card? The one that has the tens, right?
That's a 0 card. 0, 10.
0 in the middle. So I probably need a different corner. That's a good observation, but the principle stands. What you guys did yesterday is to return each card for a digit.
Too much dancing. Too much dancing.
And effectively, you return those digits back to me. So if I am to go there and look at these cards, here are the binary representation of all the numbers you had on those cards, Wednesday or Thursday, and these are the cards. And now suppose I think of the number 44 right here. 1, 1, 1, 0. But if I look at the number 44 when it appears, each one of these cards will be a bit, right? So for example, this 44 here, it's what bit? If I look at the number 44, which bit is that card?
Third to the right.
Is this bit right here, because that's the 2 to the 2 power. In fact, how can I think of one of those? Let's see if I can do this quickly. I cannot do it. Okay. So if I think of this card, right? I'm gonna do something ugly here. This card corresponds to what in this table? It's a digit, right?
Yeah.
So it corresponds to what? This is what digit?
The fourth.
Fourth.
Yeah.
Which digit?
The fourth.
This one? One more time. Is that the one?
Yeah.
So that card corresponds to that digit.
Yeah.
Every number that you pick, if it has a 1 on this digit, you would return that card. If you pay attention, the numbers on the card are exactly the numbers that have 1 on this column. So the cards you return are the digits. And the procedure is adding up the supply. Now, the last thing we have to look up here is the website, just in case you don't have it from Wednesday or Thursday. You need to bookmark this page. That's not the one. So see course.ccs.nu.edu CS1800/17F schedule. That's the address. You have a different schedule than the regular section. Everything else is the same. There's been a debate about the book. I think the overall consensus is that you should buy it online, aka from the website of the publisher, not from the bookstore, because the bookstore apparently sells the wrong version. We have a homework 1. That's our website, so a bunch of the things that you can click on, including some more notes on how binary works. Most of the exercises, if not all of them, could be done from the book. So occasionally my notes will have extra stuff in them. Like you can see, there's a lot of extra stuff that we're gonna do next week, binary search. Everything that says extra, it's extra, as it is not for credit. And the last thing is, we have a course administrator, coordinator that deals with logistics. I deal with math questions. And if you have scheduling conflicts or other types of problems, it's better to contact the coordinator. Oh, last thing, you guys need a Piazza account. So make sure you click on this Piazza link and get on the Piazza forum of the course. That's where the main student debate is going to happen. For office hours, you can come to any office hours you want. There's a big table there with everybody's office hours. I'll see you Tuesday.